Look beneath the surface of almost any crashing ocean wave today, and you will find clouds of suspended microplastics. This debris is accumulating by the millions of tons, choking coastlines and gathering in massive floating zones like the Great Pacific Garbage Patch. Today, we universally view this material as an environmental villain, a cheap, toxic pollutant that we produce in staggering volumes. But to solve this crisis, we have to look back at why we started making it in the first place. Because the material currently suffocating the natural world was originally invented to protect it. In the middle of the 19th century, manufacturing was strictly limited by what could be harvested from the earth. To make any new product, you had to cut down wood, quarry stone, mine metal, or extract bone and horn. By the 1860s, the growing popularity of billiards created a severe ecological crisis. Billiard balls were carved from ivory, and meeting that demand meant slaughtering wild elephants at an alarming rate. Elephants and tortoises were facing extinction simply to supply raw materials for consumer goods. The world desperately needed an ivory substitute to stop the decimation of these species. Enter inventors like Alexander Parkes and John Wesley Hyatt. They experimented with treating natural plant cellulose with chemicals, creating the first semi-synthetic materials like celluloid. At the time, advertisements praised these early plastics. They were celebrated as an environmental triumph, a successful method to break free from the limits of natural resources and leave endangered wildlife alone. As the 20th century began, the chemical industry moved away from modifying plant cellulose. Instead, they turned to crude oil, refining it to extract a chemical called naphtha. This diagram illustrates the chemistry. On the left are monomers, small chemical building blocks derived from refined oil. Through a process called polymerization, intense heat and catalysts force these monomers to chemically bond together into the continuous chain on the right. These new polymer chains are giant macromolecules. They lock together into complex grids that are incredibly strong and simply do not exist anywhere in the natural world. Depending on the specific bonds, you get different behaviors. Thermoplastics can be repeatedly melted down and reshaped, while thermosets harden permanently once they cool. We were no longer restricted to carving shapes out of whatever nature provided. We were engineering our own materials, atom by atom. In 1907, Belgian chemist Leo Baekeland combined formaldehyde and phenol to create Bakelite. It was the first fully synthetic plastic, containing 0 molecules found in nature. Bakelite was highly heat-resistant and easily molded. It quickly replaced expensive woods and metals in early electronics, telephones, and home radios. During World War II, plastic transitioned to a vital military asset. Materials like nylon proved critical, replacing scarce silk for parachutes and ropes. This is a 1946 chart forecasting women's hosiery production. The projected output for synthetic nylon soars past 360 million, completely dwarfing traditional cotton, wool, and rayon. The wartime factories had pivoted, bringing mass-produced synthetic materials to the civilian market. Products like these early plastic storage containers became cheap and widely available. By eradicating material scarcity, plastics democratized goods that were once considered luxuries and raised the global standard of living. But the exact molecular engineering that makes plastic an industrial miracle also creates its fatal flaw. Those giant, tightly bonded polymer chains cannot be broken down by naturally occurring microorganisms. In the 1970s, manufacturers began applying this eternal durability to items meant for fleeting convenience, like the single-use PET beverage bottle. When we try to recycle these varied products, a mechanical problem arises. Different polymer types have different melting temperatures. If you mix them in a vat, they fail to bond at the molecular level, creating a degraded, unusable sludge. Because this chemical incompatibility makes processing mixed streams so inefficient, most of what gets stuffed into dumpsters simply heads to a landfill, where it will sit for centuries. Humanity engineered a permanent, indestructible material, and then decided to use it for disposable packaging, completely breaking the planet's natural cycle of decay. We cannot simply abandon plastic. It is critical for modern medicine, for aerospace components, and our daily electronics. Instead, chemists are developing bioplastics. By engineering these necessary polymer chains from plant crops and agricultural waste, we can bypass finite fossil fuels. At the same time, the recycling industry is pushing towards artificial intelligence to perfectly sort polymers and chemical recycling processes that break plastics back down into their original monomers. Plastic was a triumph of engineering over the harsh material limits of nature. But to survive it, our next triumph has to be engineering a way to successfully coexist with it.